we have a nice way of writing the solution set for a homogeneous system vector style, and it looks like this. We know that any solution, or the solution set for any homogeneous system, has this particularly nice form, but this doesn't really get us anything for non-homogeneous systems. It sort of prompts the question, well, is there some similar nice form for solution sets for a non-homogeneous system? To get some sort of idea for what that might look like, let's actually solve one more non-homogeneous system and see what the solution set looks like when we write it vector style. So to solve this, let's write down the augmented matrix that represents this. So we're going to need 0, 1, 2, minus 3, minus 1, 1, 5, minus 1, 0, 2, 4, minus 6. Okay, and now we'll start row reducing. So I guess maybe the first thing to do is switch row 1 and row 2. So this gives me minus 1, 1, 5, minus 1, 0, 1, 2, minus 3, 0, 2, 4, minus 6. Now, let's see, we'd like to have a 1 in this upper left-hand corner, so let's multiply row 1 by minus 1. While we're at it, let's take row 3 and subtract 2 times row 1, 2 times row 2, and that's going to zero out this 2 right here. So that gives us, let's see, 1, minus 1, minus 5, 1, 0, 1, 2, minus 3, and it looks like this is actually going to completely zero out the third row. Okay. Now we're in a row echelon form, but let's go all the way to reduced row echelon form. To get reduced row echelon form, we have to use this pivot 1 right here, use it to zero out any entries above it. So we're going to do row 1 plus row 2. Okay, this gives us 1, 0, minus 3, minus 2, and then 0, 1, 2, minus 3. And then, of course, a row of zeros at the bottom. All right, so now we're all the way to reduced row echelon form. Now we can write down our solution set, or translate this to equations and then solve those equations. So we have x minus 3z equals minus 2, and y plus 2z equals minus 3. So this means that x is, so I'm going to jump straight to starting to write this vector style. So x is minus 2 plus 3z, y is minus 3 minus 2z, and z is free, so z is just z. Okay. Now we can start picking this apart in the way that we usually do for vector writing solution sets vector style. So break it up term by term. Here we're going to get one term that's just all constants. So minus 2, minus 3, and 0. And then we get a term that has z's in it. So 3z, minus 2z, and z. Okay, so this is minus 2, minus 3, 0, plus, and then this second vector, every entry has a z, so we can move that z outside. So 3 minus 2, 1, all times z. Okay, so here's what our solution set looks like. It's definitely different than a homogeneous system because rather than every term having a free variable associated with it, we have this term that is just constants. So this fixed term. There is a term that does have a free variable associated with it. But what else can we say about how this is broken down? Well, this term with the free variable, this isn't just some term. It's actually, if you go back to the original system of equations, right? If you imagine replacing this right-hand side with zeros and then solving the resulting homogeneous system, so we call this the associated homogeneous system, what would row reduction look like for this associated homogeneous system? Well, it would actually be exactly these same row reduction steps, right? What determines the steps that you take as you're doing Gauss's method or row reduction, what determines that is the numbers that show up in the left-hand piece, not the augmented column, right? The augmented column never determines the steps that you're going to take. So if we were solving this associated homogeneous equation, we would do exactly these same row reduction steps. And so the solution that you get would be exactly this piece right here. So this last term, this is actually the solutions, all of the solutions, to the associated homogeneous system. All right, well, that kind of explains this piece. What about the piece that doesn't have a free variable? Well, remember the way that we write out these solutions, you can choose any value for the free variables. In particular, we could choose all zeros for the free variables, or for the one free variable that we have. And that means that when we do this, so if we make the choice that z is 0, the solution that we get is just -2, -3, 0. In other words, this vector over here, this is a single solution to the original non-homogeneous system. So we have a single, what we don't know at the moment is this somehow a special solution to the homogeneous system? But we have, it looks like all of our solutions to the non-homogeneous system are a single solution to the system plus all of the solutions to the associated homogeneous system, which is a bit of a surprise that the solutions to the associated homogeneous system show up. At least in this example. Of course, we don't know if this always happens for any non-homogeneous system, or if there was something special about this particular system. But at least it gives us a guess, right? So we can make a guess. Maybe given a maybe for any non-homogeneous system, if you find a single fixed solution to the non-homogeneous system, then all of the solutions to the non-homogeneous system are made up of vectors that look like that one solution plus solutions to the associated homogeneous system. So this guess sort of reflects what we saw in the previous example. Of course, it is just a guess, and so to know if this really is true in general, we should check if this guess is true. And how should we do that? Well, what we can do is, first of all, we can check does every vector that looks like this, p plus h, this sort of is supposed to make you think of particular plus homogeneous solution, is everything that looks like particular plus homogeneous actually a solution to the non-homogeneous system? And then conversely, is any solution to the non-homogeneous system, does it look like p plus h, or can we write it in the form p plus h? So there are actually two things that we'll have to check, right? Really, we're checking two set inclusions. We have, is this set contained in this set of solutions, and is the set of solutions contained in this set? To do this, we should actually write out what our system looks like. So it's going to be a11 x1 plus ... down to a1 n xn equals b1, right there, down to a m1 x1 plus ... down to a mn xn equals bn. Okay, so here's our non-homogeneous system. Of course, the associated homogeneous system would be the same thing, but with zeros on the right-hand side instead of b's. Okay, so first, let's check, is p plus h a solution to the non-homogeneous system? Right. Okay. Well, how can you check if a vector is a solution to a system? You just take the entries for the vector and plug them into all of the variables. Well, it's going to be a pain to do that for every single equation, but all of these equations look essentially the same, right? They all look like ai1 x1 plus dot 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 down to ai n xn equals bi. So we can actually plug the entries of p plus h into every equation all at once just by doing it for this one sort of representative, right? Different choices of I make this equation look like any of the others. So we can check all of the equations at once, basically. All right, so let's take the entries for p plus h and plug them into this equation. So we get I1, not in, ai1 times the first entry of p plus h, but the first entry of p plus h is the first entry of p plus the first entry of h, plus, and so on, down to the last one, ain times the last entry of p plus h, but that's the last entry of p sub n, plus the last entry of h, which is h sub n. Okay, now we're hoping that if we can do some sort of calculation that shows that this is all equal to b sub I, right? We can't just write equals b sub I. That's assuming what we want to prove. So what sort of steps in a calculation could we do? Well, I really only see one option for any sort of algebra we could do to this mess, and that's distribute things. So if we distribute things, we get ai1 p1 plus ai1h1, and so on, all the way down to ain pn plus ain hn. Okay, now what? Well, with a big sum like this, there's sort of two ways to organize it. One way is to organize it by a's, so group together all the terms that have the same a, but that's actually how it started out. The other way to group it is group together all of the terms that have p's and all of the terms that have h's. So let's do that. This is just rearranging the big sum. So we have our first p term is ai1 p1, and then there's the term with p2 and a term with p3 all the way up to a sub in pn. Right? Those are all of our p terms. And then we have all of our h terms, ai1 h1 up through ain hn. Okay. Now what? Well, look at these p terms. This is actually just this ith equation, but with the entries of p plugged into it for the variables. What does that give us? Well, p is a solution to the non-homogeneous system. So if you plug a solution into the left-hand side of any one of these equations, what you get is the right-hand side of that equation. That's what it means to be a solution. So that means that because p is a solution to the non-homogeneous system, this sum here is just bi, the right-hand side of the ith equation. That's pretty nice. All right, what about all of this big sum of h terms? Well, this big sum of h terms, this is just what we get for the left-hand side of this equation when we plug in the entries of h. So what is the right-hand side? Well, remember, h isn't a solution to the non-homogeneous system. H is a solution to the associated homogeneous system. So that means if you plug in the entries of h into this thing, you don't get bi, you get 0. So what we get here is bi plus 0. In other words, it's bi. So we plugged the entries of p plus h into this ith equation, and we did, in fact, get b sub I. Right? That means that p sub h really is a solution to this non-homogeneous system. So that means everything in this collection is a solution. Good. Remember, that was half the battle. Now we need to check, is everything that is a solution in this collection? So, right, now we need to show every solution to the non-homogeneous system is of the form p plus h for some h, which is a solution to the associated homogeneous system. Remember, the vector p is fixed. We can't change p. What we need to do is find a homogeneous solution, or a solution to the homogeneous system, that when added to p gives us this solution for the non-homogeneous system. Okay, so to start out, let's let v be a solution to the non-homogeneous system. Okay, so right, what we're hoping, so let me, over in the margin, let me write out what we're hoping. We're hoping that v is really p plus h. We don't know what h is at the moment. That's the problem. But if v really is p plus h, that means v minus p is h. So, right, this is what we're hoping is true. But if that's true, v minus p should be the h that we're looking for. So maybe what we should do is think about v minus p. What is v minus p? So let's consider v minus p. Now what we're hoping, again, is that v minus p is a solution to the associated homogeneous equations. Well, we can check if it is a solution to the associated homogeneous equations just by plugging v minus p into the equations. So let's do that. And we're going to do that in the same way that we did in this first bit. We're going to just take the entries of v minus p and plug it into this left-hand side here and see what we get. Okay, so to do that, we get, or when we do that, we get ai1 times the first entry of v minus p, which is v1 minus p1, plus, and so on, out to the last entry, which is ain. Gotta be careful to get your indexing right. ain times the last entry of v minus p, which is vn minus pn. And now we're hoping, right, we're hoping that this is 0, right? We're hoping v minus p is a solution to the associated homogeneous system, so we're hoping this produces 0. So let's see if it does. Well, you can kind of see we're in a similar algebraic situation to where we were at earlier. We don't have that many things to do. All we can try is distributing the a's, and then regrouping. So let's do that. We get ai1 v1 minus ai1 p1 plus, and so on, down to ain. Oh, my computer's thinking about something. This is not a good time, computer. Uh-oh. OneNote just crashed. Great. It's probably not a good sign. Stand by. Okay, good. We didn't lose anything. Okay, and we're back. ain times the last entry of v minus p, so vn minus, AIN times VN minus AIN PN. Okay, now again, let's regroup. Let's group the V's and we'll group the P's. So AI1 V1 plus all the way down to AIN PN. And now for all of the terms with P's, well, all of the terms with P's have a minus sign in front. So let's factor that minus sign out all the way at the beginning. And we get AI1 P1 all the way down to AIN PN. All right. So now what is this sum? Oh, this P should be a V. Sorry. Okay. So what is this big sum of V terms? Well, remember, V is a solution to the non-homogeneous system. So here we've essentially plugged the entries of V into the ith equation. And since it's a solution to the non-homogeneous system, that means we get the right-hand side of the ith equation, which is B sub I. Okay, minus. Now what is this? Well, P is also a solution to the non-homogeneous system. So here we've plugged the entries of P into the ith equation. That means we get the right-hand side of the ith equation of the non-homogeneous system, and that's B sub I. And B sub I minus B sub I, that's 0. So what we found here is that plugging the entries of V minus P into the ith equation gives us 0. So that means that V minus P is a solution to the homogeneous system. Just like we were hoping, right? So we can really call this H now and not confuse ourselves. The letter H we've sort of been reserving for solutions to the homogeneous system. Now we know V minus P is a solution to the homogeneous system, so it's okay to call it H. And now V is equal to P minus P, sorry. Right, what we want to end up with is V is equal to P plus H. Okay, so V is equal to V plus P minus P, right? That's obvious. I'm just sort of uncanceling a P. But then we can rearrange this, write it as P plus V minus P, and that's P plus H. Right. So what we've done is we've successfully expressed this arbitrary solution to the non-homogeneous system as this particular solution to the homogeneous system, non-homogeneous system, plus some solution to the associated homogeneous system. So this shows that not only is, if we go back to our original guess, not only is every vector of this form a solution, every solution to the non-homogeneous system is of this form for some choice of solution to the homogeneous system. So the slogan version of this is that for any linear system, homogeneous or not, every solution is of the form particular plus homogeneous solution.